My name is Jeff Merkel. I'm a teacher over at University of Colorado, Denver. I teach in both physics and recording arts. Kind of Jack, I guess, I don't know. I teach acoustics, like physics, sound, and music, and I teach audio production. I also run a recording studio, recording, mastering, and post house called 8 Houses Down, and it's right downtown Denver. I kind of do a lot of things. And then I also have, I run this spin-off company called Denver Drum Room, which you probably just saw here. So this is another, I specialize in recording drums. We do a lot of that. I'm the mastering engineer there. But I also run a loudspeaker manufacturing company called Merkel Acoustics Research and Design, where we do, basically we make, well, we design and do high-end loudspeakers, but we also do acoustic treatment and well, kind of the subject of today's talk. Doing just basically kind of acoustic measurement stuff. And then I also do, I also just now started a group called Signal to Noise Audio Labs. So if anybody's interested in joining, it's basically an interdisciplinary research collective that makes cool shit. So that's what we do. Like, basically, we do everything from acoustics to making your own instruments to making anything cool. And kind of the idea behind it is to take scientists, engineering, and arts and put it together and see what comes out, kind of like MIT Media Lab. So we've been having that thing going for a little bit now. We just kind of got off the ground, and we're doing some really, really fun stuff. And you'll actually get to see a little bit of the stuff that we're doing right now. So, so that's just kind of my thing. So my life is audio. I do sound all day, every day, in every form and fashion. So both at school and at home. My studio, I also live at my studio, which is like at 29th and Walnut. So I'm around sound all day, every day. And yeah, so this is my life. So I wanted to talk today about ringing out your room, and specifically about Room EQ Wizard and some of the tools that come out. So basically now the tools to do speaker and room measurement have become readily accessible to everybody out there. If you have a computer, you can run this stuff. So the problem is, what I've noticed on the forums, well, just as a show of hands, anybody used Room EQ Wizard before? Okay, yeah, well then that's what we're going to play with today. So there's a handful of you out there, and there's a whole bunch of other software out there besides Room EQ Wizard. But Room EQ Wizard is just amazing, and amazing for so many reasons, for technical reasons, but amazing because it's free. So we're going to go run through, kind of do a quick tutorial. But what I've noticed is spending time on the Room EQ Wizard forums, or Home Theater Shack is where the forums where you get this stuff, is that I see so many people getting measurements and going, what does it mean? So what I kind of want to do is demystify this stuff just a little bit. So what we're going to go through today is talk just a little bit about, do some measurement tools and methods. And then I'm going to spend about the first half of the talk on measurement and tools and methods. And then the second half, we're going to talk about analysis and theory, specifically low frequency. And honestly, I mean, we're trying to do acoustics in a nutshell. We don't have time for everything. So we're only going to really focus on the low frequency, specifically room modes, just because I have this killer demo. I really want to show it off. I think it's really fun. So the high frequency stuff is a little bit easier to understand and a little bit easier to get through. So we're really going to spend most of the time talking about just this notion of room modes. And I'm going to talk a little bit what low and high are. Because I mean, what's the difference between low and high? Low is when we talk about this low, high, hot, cold, those are relative terms. So when I say something is hot compared to what? Well, hot compared to your skin temperature if you put your hand on the stove, certainly. But when we talk about sound, we need to kind of define what the difference between high and low is and where that definition comes from. And we're going to talk just briefly about treatment. Unfortunately, again, we only have an hour to really hammer on this stuff, so we're really not going to get to talk about treatment too much. But what I will do is send you on your way to find the information that you need to if you want to explore the stuff further. So with that in mind, the first thing I want to talk about is this notion of speakers in rooms. When we talk about a speaker, it's so easy to look at just the speaker, I guess, measurements and go, is this a good speaker or is this a bad speaker? But what we really need to understand is that we're talking about a larger system here and a speaker in a room. So when you have a speaker in a room, especially in small room acoustics, and we'll define what small is again here in just a moment, that you have to do that the room and the room itself is part of the acoustic system. And so to really understand and appreciate how well your speakers are working, you need to understand what's going on inside the room there. So we have to approach this speaker in a room as a single large system. It's a very complex system too. So we're going to try and break it down in a little bit, just so we can get a firm understanding of what's going on there. But again, I just want to really emphasize that when you look at speaker specifications, say, or measurements, or statistics or anything, you have to take that with a grain of salt, because you can say, like, how's this going to perform in my room? And actually, Floyd Toole has done a ton of work on this stuff. This is one of the suggested reads. If you're into this stuff, this book came out a couple years ago by Floyd Toole, and he talks a ton about how to place your speakers in your room. So we're not going to talk about how to set up your speakers in a room. We're just going to talk about how to measure your room and your speaker setup. So again, the idea is here we're trying to look at this as an entire system, not just the speakers here, because when you're upstairs or in some of these rooms around in here, and I've seen a lot of really good treatment throughout the rooms here, but we're dealing with a tough situation. We're dealing with some relatively small listening rooms throughout the space here, and sometimes they have a lot of acoustic treatment, sometimes they have none. And to me, it's really hard to get a true sense of what I'm hearing. When I sit down and listen to some speakers upstairs, like, am I hearing the speakers or am I hearing the room? And the truth is, you're hearing both. But what's good, what's wrong? So and sometimes people are taking that into account and actually treating the room. Sometimes they're not, and they're just letting the room raw. And so, which to me is a pretty tricky thing. Because I guess the underlying theme here is that your speaker setup is only as good as the acoustics in your room. So you need to spend, in fact, I would go so far as to say you should spend as much on your acoustic treatment as you do on your speaker and amp setup. Well, maybe not spend as much. Maybe spend as much time as on that, because yeah, you can spend a lot of money. But so I wanted to try and incorporate how this room works with our speaker room setup here. So the first thing we're going to talk about is room measurement tools and techniques. So with that, I'm going to switch over, and we're going to actually just dive into Room EQ Wizard. So Room EQ Wizard is free software by, I can't remember the guy's name. It's like one dude who writes the entire software thing. He's in Britain. And he's really responsive on the forums. You can actually chit-chat. I've had some things like issues with some of the software, and he'll actually go through and fix it, in a couple weeks during the next release. So this is Room EQ Wizard 5. One of the things that I love and both hate about this software is it's Java-based. Java-based is kind of annoying because it takes a little while to load, but killer because it runs on anything. So if you have a Mac, if you have a PC, if you have Linux, so actually I'm very Linux-based here, it runs just great on Linux. So you can use any system you have, and it doesn't need to be the most powerful thing on the planet. A laptop is certainly easier because you move stuff around. So let's talk about some of the tools. So let's start with the software here. So the software itself, you can go to hometheatershack.com, and that's actually where you get the links to do this. I'm not going to write right now because my handwriting sucks so bad. You'll be like, what did you write? So, it's hometheatershack.com, or just look up Room EQ Wizard, and this comes up. Honestly, it's a terrible name for the software, because for as cool as it is, that's a pretty lame-sounding name. But this is what pops up when you open it. And so it just pops up, and it's just this kind of blank workspace. So before we dive into getting to the rest of how we're going to start working with software, let's talk about other components that we need. So we need some sort of way to control our speakers. So the hometheatershack.com is actually very geared towards home theater type stuff, but it holds its own in other areas, audiophilia or pro audio and that kind of stuff too. So, but we need a little bit more hardware to go along with this stuff. So we need some way to we need a speaker to excite the room and to test our system with. So Adam was so cool enough to let us use this. So we're going to do some speaker and room testing with this right here. So we have our speaker, and then we need some sort of amp. I have this rig up here. So if you want to come up and look at this later, this is kind of my speaker testing rig. It's actually, I have a Behringer DCX2496, which I don't really like that much, but it's really, really handy for what it does. As far as like crossover testing and some of the points and filtering and so on and so forth. Then I have this really kind of complex web of wires in here and switches and stuff so that I can quickly switch between doing impedance measurements and because I do this for loudspeaker. This isn't just for acoustic measurement. In fact, I'm a loudspeaker manufacturer, so I do more speaker measurement than I would say room measurement, but it works just fine for that. But I have all these switches and all that kind of stuff down here, and then I have an amplifier down below here. But you could just as easily use any of your home amplifiers that you have, either fancy pants ones, like really, really high-end ones, or you could use just kind of your typical lower-end home theater tuner type style thing. However you have your set, and the idea is here, you're going to test your setup in situ. So you're going to test it up as you're actually listening to this thing. So then we're going to need some way to get the sound in and out of the computer. Now, the software goes through, and on the forums and the help areas, they talk about all these different ways you can use to build your own cables and using just the 1/8" stereo inputs and outputs on your computer. And that works, but I lobby pretty hard in the other direction in that I really do believe that you should have some sort of external sound card. In the case of this one, I have a USB M Audio Fast Track Pro. I use this thing all day, every day for teaching, for loudspeaker measurement. You can get some really, really amazing results out of just this little device right here. So this guy costs about $200, but you can get something equivalent to this that has a little bit less bells and whistles for on the order of $100. So for $100, you can get a nice USB type, and I've seen a lot of other ones around the show here as well. But for $100, you can get something like that. And then we need some sort of microphone. So starting at the low end, you can just get your Radio Shack Sound SPL meter. It has a RCA jack out on the side right here. And you can actually use this as a measurement microphone. Not really probably the best thing on the planet, but for whatever, $50, $60, not too shabby. So what you would do is you have the RCA output here, and it would go to the input here. So it sits on, I have this as just a camera, little tripod. So this actually mounts on camera tripods, which is cool because you don't need to go buy mic stands or anything like that too. So it is pretty handy. But if you want to move up and the next level up, we can go to actually using measurement microphones. Because I have a pro audio interface here, it's able to supply phantom power and add a significant amount of gain to these things. So this is an older Audix measurement microphone right here. This is the newer Audix measurement microphone. So this is the TM1. This costs about $300. This is, I would say, considered like the low, mid-level kind of measurement microphone. You can get the Dayton Audio through Parts Express out there, sells one of these for $50 with a calibration file and I think shipping included, which is just an amazing steal. So highly, highly recommended if you want to get in on the budget with this sort of thing. Whoop, sorry. So I just have these little tripods because when I do teaching at school, I have these sitting up on the table oftentimes. But for this, I brought in a real mic stand. From here, if you want to go up higher and start doing really, really high-end measurement microphones, you can start going to the Earthworks and on up. Earthworks starts at about $600, and then your really crazy, exotic, laboratory-grade stuff starts going up to thousands of dollars. But truth is, for any of the kind of stuff that we would probably be doing, I find that this level of microphone is just fine. The cool thing is with this one, I bought this one from Rational Acoustics. If you buy that mic from Rational Acoustics, they give you a calibration file along with it. So the cool thing is, even though these are not necessarily the best microphones, we can compensate for their lack of frequency response. So what we're looking for in a measurement microphone is ultralinear response. Because we want to measure the microphone, or we want to measure the speakers in the room. We don't want to measure what's coming out. If our microphone's not perfect, we don't want to measure a nonlinear microphone. So our goal is to get the flattest microphone possible, which, as you can probably guess, gets very, very expensive very quickly. So what you can do is if you take something that's maybe subpar, you can compensate for those differences and just get a calibration file. The cool thing is, with the Radio Shack one here, there's umpteen quadrillion of these things throughout the world. And the fine folks at Room EQ Wizard and the larger audio community has gone through and actually done a billion different reference files on these things and come up with these actual calibration files. So if you buy this and you want to use this, you can use it. You can just go download off of radio or roomeqwizard.com. You can download the calibration file for this. Now, granted, it's not going to be perfect, but it'll get you within a couple dB of linearity, which is pretty good. So this one comes up, will be a little bit smoother off the bat, but it also has a calibration file along with it. So for that, we're going to plug that back in here. And then the last thing that we're going to do in this is actually provide a loop back. So what I'm doing is I'm taking the output, and I'm looping it back to the input. So if you're going to do this with your own cables, you have to basically create a loop back. So, and the idea for the loop back is to create a reference level. So you're going to take, I guess I don't have a slide for it, but basically you're going to have your two outputs and two inputs. And one of the outputs goes back to the input, so it knows exactly, both for timing and for also nonlinearities, what's going on with your sound card. And then the other one, the output goes to your speaker, and the input comes from the microphone. So now we have two different inputs to test. We have our device under test, DUT, and then we have our loopback as our reference level. So that's essentially how we're going to set this thing up. So you can't, well, I'm going to have to make this off the screen just a touch. So the first thing I'm going to look under is my preferences here and just take a look at, oops, they can't show up over here. So here's my preferences. Wow, big over on the screen. So the cool thing is in the latest revision of Room EQ Wizard, you can use ASIO ASIO drivers, which before you couldn't. You can only use Java stuff. Java stuff is cool. It's just a little clunky and slow. As a word of warning, though, if you're using this with a Macintosh, you can only use an interface that has no more than 2 inputs or outputs. I can't remember which one it was. But if you have a multi-channel, say something that has 8 inputs and 8 outputs, you can't use it with a Mac. And everyone's kicking and screaming on the forums, but it's not the developer's fault. It's actually a Java Apple thing. So until they fix Java, or I'm sorry, until Apple allows Java to do up the inputs, you can't use it. And I've seen this happen a number of times with helping people out with this stuff. They're like, why isn't my inputs not showing up? And it's because it's one of those rare instances where Macs don't work very well. So in this case, I have ASIO, so I can choose my M audio driver here. I'm choosing my analog out to analog in, analog 2 to analog 2 in. Cool. If I want to throw a calibration file for my sound card, I can create one and make one right here. I don't need to. Levels, I'm not going to do this right now. I'm going to check my levels in a different way. Mic meter. So here's where actually I would load in my calibration file if you have one. So the cool thing is with that Audix run right there, they actually sent me a calibration file from Rational Acoustics that I just loaded in right here. If you want to, you can actually clear it, and you don't have to use it if you don't want to. If you want to use a C-weighted SPL meter, that's a crude calibration for this guy right here. And then if you want to start throwing house curves in there, we're not going to really deal with a lot of this stuff. I'm only going to have time to talk about like the super top level on this software just because it gets pretty big pretty fast. So the first thing I want to do is, okay, so I'm going to actually, let's get this set up. So we're going to actually test this setup here. Now generally, if I'm doing loudspeaker testing, I test either 1 or 2 meters off the front of the speaker here. So, but again, that's for speaker measurement. That's not necessarily for room measurement. For the room measurement, I'm going to actually get a little bit further away. And in your case, if you're doing this at home, you should have your speakers in their normal position, and then you're going to test. You're going to measure from your typical listening position. But you're going to actually move it around a little bit too. So we're just going to assume that this is a pretty crummy listening position for the speaker. Why? What's wrong with this listening position? Sidewall, yeah, wicked reflection right here. So, but hopefully that'll show up in our measurement here. So first thing I want to do is actually get some levels and make sure that we're going to be all good. So I'm going to start with the generator. Probably showed up on this screen. Bring it over. Just to make sure that we're in the ballpark. Make sure that everything's actually working the way it's supposed to. OK. So here we have our output. This is the mic input, and this is the reference input. I think I have the gain cranked on this, so we're probably getting some noise. Let's just go ahead and press play, see if we get some sound. So it starts at really quiet, so you don't tear your head off. And I actually have the speakers down here. We want to go up to, let's go up to -10. I'll do everything around -10. OK. So we're looking pretty good here. I could up my gain on the second input a little bit. Actually, I'm going to do noise. The sound of sine waves. Cool. Now we're within ballpark of working range here. We know that at least our inputs and our outputs are working. If they're not, then of course that's where you're going to have to spend a fair, honestly, that's for if you guys that said you tried it. Did you get past this point? I mean, this is usually the sticking point right here, right? Just getting to this point is usually the hardest part. This is kind of like Adam's presentation just before. This is like a cooking show where we have everything kind of rigged so it works, So when you're doing this at home, because I don't know, when you watch cooking shows, you're like, dude, I could totally do that. That takes like, what, 15, 20 minutes? But then when you're actually doing this at home, you have like, got to find every freaking cable under the sun, and you obviously don't have one that you need all the time. And so this is a canned performance, so to speak. So, but it does work. And once you have, like for me, at least I have this guy all wired up and preset, so I can actually take this thing on the fly, and I can go do measurements whenever I want, wherever I want, pretty quickly. So, okay, next thing I want to take a look at is using this as an RTA, a real-time analyzer. So an RTA is just a quick way to do some spectrum analysis. Oops, lost my signal generator. Guess I can't close it. My wife hates that sound. I listen to it all the time. I listen for my master's thesis work. My master's work was on loudspeaker design, so I spent an entire summer listening to pink noise. So, and also just the chirps, which we're going to be doing impulse responses. Like my wife hates it. All last night when I was getting ready for this, she's like, "Really? Do you have to do that tonight?" So what we're looking at here is we're looking at basically an EQ curve of the performance of our speaker here. The problem is, and I don't really like, real-time analysis doesn't give us a whole lot of picture. First, it only gives us one dimension I guess it only gives us one dimension. It only gives us frequency. It doesn't give us anything about time or any time information. And when we talk about speakers and speakers in rooms, we really have to concern ourselves with time information as well. But just looking at this, we can see, oh, it doesn't look too bad right there. And we see something all the way, it's going from 10 to 20K right now, maybe up to 30K. Yeah, well, I guess I'm 48K, so it's only going to 24K sample, or 48K sample rate, so 24 kilohertz high-end frequency. So it's hard to like look at this and actually really understand. We see some trends here. We see lots of little tiny fuzzy hairs. And a lot of times people start freaking out about that sort of thing. But truth is, you can't get too concerned about that. If we want to, we can start smoothing this thing out. If we want to kind of fix our data, make it look better, we can start smoothing things out. So if we smooth it out there, looks a little bit. We still see some sharp peaks and some valleys here. And at this point, we're going to be going, okay, well, how much of this is the speaker and how much of this is the room? Because we have to consider that this is not just a speaker to microphone instance here. We have a speaker to the larger room going on here. So if we want to just keep smoothing things out, we can. But it's again, it's not going to be really giving us a ton of information. This is really helpful if you're say working in live. If you're mixing for a live show, this is a great way to get some quick measurements and real-time measurements. Because an impulse response is not done real time. So so with this, if you wanted to EQ in real time, you can just have your EQ set up, and then you can bump up your low frequencies if that's what you see as a problem. Yeah.
Is that speaker really giving? And I understand maybe it is
sure.
usable output down to 10 hertz.
No. So there's probably also just a lot of interference and rumbling and so forth down here. So I mean, there are room modes, and there is stuff going on down to 10 hertz, but at that level, probably not. And so we'll see that. And again, that's why this RTA is just kind of I think is a relatively crude measurement. It's a useful tool, but a crude measurement. So, but again, for crude, if that's good enough for what you're doing, or if you're trying to monitor something in real time, you can do that. So I can actually just run this thing in real time. And of course, without a signal, we can watch my voice. Let's reduce the resolution or increase the resolution on here. We should be able to see the harmonics of my voice. Let's go even further. So we can see some of the harmonics. It's a little janky, but you can start to see the response. There's a lag in this response. So when you start talking about not sampling theory, but measurement theory, we do what's called the Fourier transform, when we're converting time domain information to frequency domain information. And so what we're trying to do is we're trying to image our sound. So it's taking time information. So sound we usually think sound as a function of time, and we're converting it to visualize it as a function of frequency. But the problem is, for those really low frequencies, they take a long time to go through. So for a long time for that wavelength to pass you. So if you're waiting for a very, very long time for that wavelength to pass you, a lot of information can be happening at those high frequencies that are very much quicker. We'll talk a little bit more about that in just a second. Okay, but the idea is that we don't really want to do too much with the RTA here. What we want to concern ourselves more is with the impulse response. So what we're going to do is take some measurement responses here. So we're going to take this, and the cool thing is, and we're using this today as mostly as a room and speaker system device, but you can also use this just as a speaker measurement tool. So we can actually do complex impedance with some calibration. So I have my setup here, so we could actually go through and for kind of continuing on with the last talk, if you start building your own speakers and you want to start understanding what's going on and how it's working, surprisingly, when you do a lot of your own speaker building, very little of it has to do with acoustic measurements in general. When you're designing your speakers, most of the measurements come from electrical measurements, and in particular, our impedance measurements. So much of your speaker design, if you want to get a really, really, really dialed speaker, you end up having to do most of this with math and with numbers and electrical testing. And acoustic testing is the very last thing that you do. So we can go through and we can do full complex impedance measurements with this. So you can do, and you can get full teal small parameters out of this. So they have all these tools. We have SP limiter, logger, generator, RTA, teal small parameters, modal simulation, which we'll spend some time on today as well. So it's a very, very sophisticated tool, and it's free. I know, it's just crazy. This software to me, this should cost $2,000. Like, that's about how much this stuff is worth. So, and like I said, there's other tools out there that do this too, but for free, I mean, and it looks good and it works really, really well. Okay, so we're going to go from, let's go all the way down from 10 to 20K. Let's do a minus 10. Let me get out of the way so we can start measuring here. I'll be real quiet. So what we're going to do is we're going to do a swept sine pulse here, or swept sine impulse, and we'll explain what that means in just a minute. All right, so we have our first measurement taken. Now, the tricky business. What are we looking at here? So in general, it gives you what's called your SPL and your phase. So what we're seeing right here, this purple line right here is our phase, and our dark purple line in the background is our I guess what we call our levels. So the phase is a little tricky when you first look at this. You're trying to understand what's going on there. So, well, actually, let's just talk about what the impulse is for a moment. So if we look at this impulse, and we zoom in on this thing, an impulse, let's talk about what an impulse really is. Our goal here is an impulse is all the frequencies of the spectrum at the exact same time instantaneously. So what we're trying to do is go. So when I clap there, what we're doing is we're exciting the room modes. And it's also exciting all the speakers, the diaphragms, the air, everything inside of here. So we're exciting all of this information at once. The problem is, and you can certainly do that. We can pop a balloon, or we can take smack something and create an impulse, because we're trying to excite the room modes in here and excite all the frequencies at the same time and see what happens afterwards. The problem with that is that's just a very tall order for a speaker. So what we do is we actually do this sine sweep. And as we go up, we go, we're measuring the amplitude at that certain frequency. And then what it does is this transform folds it back into 0 time. So as it goes through that entire sweep, it knows when it did that. Well, that's what that loopback is for. It knows when that sweep was happening, and it takes that amplitude and folds it back in time to create a single impulse right here. So this is the equivalent of doing a big bang in the room, and this is what comes out. So what we have is our big bang, and we see all this information coming out afterwards. So, and from this, so we're looking at time information right here. We're going to do a Fourier transform and look at the frequency information, and then we can also have time information. So this is impulse is really cool because it gives us both time and frequency information. And what we're doing is just there's a lot of different kinds of transforms here, but we're going to do an FFT, a fast Fourier transform, which is basically where it's just a mathematical method of switching between the two different domains or transforms. So, but usually when you're looking at this, you don't really need to spend much time except to make sure that, yes, I indeed got an impulse there. You really wouldn't be looking at that too much. So if we look at our all SPL right here, I'm going to close this to make it a little bit smaller so we can actually get a little more real estate here. And let's move this down. That still doesn't seem like it's giving us a whole lot of information. So what I'm going to do is to throw a little bit of smoothing on here. Now let's take a look at Okay. So that's still pretty high resolution. I would say, in general, don't concern yourself with these crazy, crazy high resolution measurements. Let's actually go down to like 1/6. Because what we're looking more for is trends here. So this is going to be the frequency response of this speaker in this room right here. So if you're sitting here listening, that's what you're going to be hearing if you play pink noise out of here. Now, actually, that looks pretty good. We do see some bumps here in the low frequencies. So now we need to start considering ourselves what's considered high and what's considered low, and why do we care what the difference is. When we talk about the high frequencies are going to be high frequencies are small wavelengths, low frequencies are long wavelengths. When we get into low frequencies, the wavelengths are going to be in the same scale as our room. We talk about high frequencies, they're going to be much smaller than our room. And what we consider high and what we consider low depends on what room you're sitting in. And we'll go back to PowerPoint, mess around, and do some measurements on that to determine that. But in general, and John was talking about this before, he's like around 300 hertz is where, and it depends on what room you're talking about. Around 300 hertz or 200 hertz down is where it's going to start getting to what we consider low frequencies. And around that range up is what we consider ourselves high frequencies. So this is why we call this small room acoustics. Small room acoustics is when the wavelengths, of course, are on the same about level as the room you're sitting in. If you're in an auditorium, a large hall, those walls are so far apart and the ceilings are so tall that those wavelengths, those standing waves, those modes in there are so low that they don't cause any problems. And so pretty much everything in a room like that would be considered high frequencies based on this definition I just created. So what we're going to look at here is, and we're going to concern ourselves mostly with the low frequencies here. But let's take a look at what else other information we can pull out of this. We can look at our RT60. So it calculates our RT60 for us. So this is a little confusing when you're looking at this for the first time. My toolbars are hard to see. Oh, those are really dim. Oh, because they're not there. So the controls on this thing, you middle click and move around, and I'm all thumbs when it comes to this. Zoom out amplitude. Okay. So if we look at this, what we're looking at a bunch of different kinds of RT60 down here. We have our T30, our T20, and what those correspond to, I'm not actually going to go there. we can basically get a basic trend right here. It gets a little more complicated. But what we can see here is that in this room, we're having around about a 0.5 seconds reverb time. That's pretty high. So, and we can see it as a function of frequency. So if we look at it around well, something's huge at 80. So it could be an anomaly. It could be actually something that's going on. We need to investigate this a little bit more. But along the lines here, we see that we're hovering around about half a second, and then it bumps up down here and then trends down below here. So we can start to see that there's some sort of trend going on here. So when we talk about reverb time, RT60, how long it takes the sound to drop 60 decibels, it's not the same for all frequencies. And so when you go into a room and you say, oh, it's a live room, or it's a dead room, or something like that, well, that's not telling you the whole picture. It's only telling you it's in general, overall, average live or average dead. But we need to think about this in terms of actual frequencies and frequency dependence. So it's actually going to be high. It's going to be live or dead, depending on what frequency you're talking about. So what we could say is that around 2.5K is a lot more live than down here. Again, this is not a very good listening environment and I'm not trying to draw any huge conclusions out of this yet, because we need to do some more measurements here and take a look at this a little bit closer. But we can start honing in on some overall ideas. The next up is we want to look at, well, actually let's just go to waterfall. Let's look at this. So this is what the cumulative spectral decay here. And we can look at how long. So now this is where the time component comes in. So we're looking at time in this direction, frequency in this direction, and amplitude in this direction. So what we can see here, wow, we can actually see some pretty interesting stuff. I'm going to scroll this down a little bit. Oops, maybe not that much. It's easy to freak out when you start seeing this, but I can make it look a lot better, right? Oh, wow, looks really good. Well, here's some interesting stuff. Actually, it's really quite interesting. So what we're looking for, and again, going off of what John was talking about a couple hours ago, was we're looking for ringing. So whether in the high or in the low frequencies. Generally, what you're going to see is this is going to be part of you. This is going to be your loudspeaker response, and sometimes your room response. And the low frequency stuff is going to be really, really your room response here. So, sorry for you guys in front there, but what do we see here? I mean, do you guys see those really long, sharp peaks that are hanging out there? That's bad. We don't want to see that. I can't tell if they're harmonics of one another. Kind of tricky to tell. That's like, wait, so this is 60, 80, it's a little harder to tell, 60, 80, 120. So it could be, well, that's kind of a weird resonance. It's hard to like work back and figure out exactly what that is. You have to look at your materials and so on in this room, but you can actually start to draw some pretty interesting information. That's kind of bad. So we're going up from 0 to 600 milliseconds right here. So that's 0.6 seconds. Our goal in most acoustic environments is we want to see uniform, smooth decay at all frequencies. That's our goal. Different people have different preferences, but by and large, that's what we're looking for, at least in the high frequencies. In the low frequencies, it's going to be really hard to do something like that. So let's take a look at, let's do a couple more measurements here. So let's get back to SPL. And what I want to do is I want to move the microphone around a little bit. Because what we want to start to look at also is we're trying to determine how much of it is the speaker and how much of it is the room. And truth is, when you have a listening space, some of us are lucky enough to have a dedicated listening room with your speaker sitting in the sweet spot. Most of us have living rooms, and we use it as a multi-use room. So you're going to have multiple listeners or a home theater type thing. You're going to have multiple people throughout the room. So it would make sense to move the microphone around and take measurements at different areas in the room. So let's actually just move it over a little bit to the wall here and take another measurement. All right, so let's take a look at that. Looks good. Do a little smoothing. And from here, what you should probably do is keep all your data and notes about your data over here. So I have a naming algorithm here, and then I'll go through and I'll save my data, however you want to save it, and then keep a record of your stuff as you go through. And this system is really clean and really easy to do. So I'm going to move it one more time, and hopefully it doesn't cause us a problem. If it does, whatever, we'll deal with it. But you'll see why I'm showing you this. All right, what I was doing 1/12. Yeah, let's do it again. OK, so now what you do is you start moving this thing around. We can start to see what's different as I move position. And for loudspeaker, what I do oftentimes, I'll have it 1 meter, and I do polar responses. So I'll move it. I have a thing. I move it 5 degrees and take tons and tons and tons of measurements. And you can optimize your crossover. You can optimize your crossover region. You can optimize your baffle width and your curves and all this kind of stuff. And you can get a lot of information out of this. But we can see certainly that there's some. What's the same and what's different? We're seeing a big peak right here at. I can't see what that is. Peak at about 90 hertz. So something's going on there, and that's a fairly low frequency. So I imagine that there's some sort of reflection, some sort of destructive interference going on there. But above, as we get below 1K, we start to see some weird differences there. Some of that's going to be this is bad because I have a reflection right here too. So we're going to get some weird reflections off the top here and off the screen, and all sorts of weird things start happening. So again, this is not a very good acoustic environment for what I'm trying to test right here, but it gets the idea done here. But here's what's pretty interesting and what I think is really cool, is if I get all these responses together, if you start taking them all over your room, you can go through and average your response. So I can find the average response in my room and go, okay, this is in general what I'm working with. Because if you start dealing with too many variables and too many things at once, your brain's going to explode. So you want to try and keep this thing concise and work with this a little bit. So from here, you can start making some decisions on how you're going to treat your room. So with that, I want to switch back to some PowerPoint stuff here. I'm going to kill this. Go away. Mousing here is hard. No. Now let's get back over to where we left off on this, because I want to start talking about how we discover what our room modes are. We hear about that. We hear about room modes often, and we see diagrams of it, but I really want to spend time and get those to internalize. So again, to define the difference between high frequency and low frequencies are where we start getting standing waves in your rooms. So what frequencies do we care about? Well, we can hear from 20 to 20K. So truth is, if we can't hear below, if something weird is going on down below 20K, we don't really care. Or 20 hertz. If something's going on above 20K, we don't really care. Now there's exceptions to every rule, and there is weird interference in the supersonic that comes down into our audible range, and infrasonic stuff that comes up into our audible range. But for right now, what we really concern ourselves about is between 20 and 20K. So let's talk about this good old equation. This equation, V equals F lambda, there's a number of my students here, see this, and especially my physics students, see this equation all the time. V equals F lambda. So one of these kind of classic physics equations, and it holds true for any wave. We care about sound, but it's true for any wave. So what that means is velocity equals frequency times the wavelength. The beauty is when we're talking about sound in air, this V is pretty much fixed. And what's V? What's the speed of sound? All right, but we're going to play with the rest of the world, so we're going to do this in SI units. So anybody know what the, like not feet per second, but meters per second? 340, 343? V equals 343 is what I teach, meters per second. It depends on temperature and elevation and all these other things, but it's roughly 343 meters per second. So we can use that as kind of our working number here. So what is a frequency is how many cycles per second, and wavelength is how long a single wave is. So with this, the cool thing is that if we look back at this equation, though, we know velocity. So now we see that if we change frequency and wavelength, that if our V is fixed and our wavelength goes up, our frequency goes down. So this is a relationship between these two. So frequency and wavelength are very, very, very tightly connected. Well, I guess physically. So let's do just a really quick one. What's the wavelength of a 1,000 hertz sine wave or wave in air? So we start with V equals F times lambda. We're solving for wavelength here. So lambda equals V over F. So we do 343 divided by 1,000 hertz. And we end up with 0.343 meters or 34.3 centimeters. So a 1 kilohertz wave is about this big. So if you sat into my talk last year, and much of my life revolves around this understanding how long these wavelengths are. So when we want to talk about how long or how short these wavelengths are, really depends on how the sound is going to behave in a room or off of a speaker or outside. So let's take a look at some key wavelengths here. 20 hertz, 17.2 meters. Big, real big. So is 17.2 meters big or small compared to the width of this room? About the same, maybe a little bit bigger, but on the same scale. Compared to you, it's a lot bigger. But then if we go to the other range, what's 20 kilohertz? 20 kilohertz is 1.72 centimeters. That's teeny. Right? It's about that big, plus or minus. But it's teeny. In fact, I'm big compared to that wavelength. Again, and then this has to do with all head-related transfer functions. We start talking about localization and how we hear high frequencies and how we hear low frequencies compared to our head. Another day, though. So 200 hertz, 1.72 meters. So that's about 200 hertz. And 2 kilohertz, 0.17 meters or 0.17 or 17.2 centimeters. That's about 2 kilohertz right there. So what we care about is when we start talking about these really, really low frequencies, and what we care about mostly are going to be this notion of standing waves. So a standing wave is when something resonates. So in the case of a room, our wave is going to start bouncing back and forth here. In fact, I have a little animation for this. Because what you have to do is, sound is tough because you can't see it, right? So you have to kind of use your mind's eye to envision what's going on. And we draw these graphs all the time. But really, you need to go back and go, what is that graph or plot or whatever describing? And usually it's in something in air because we can't really draw air very well. So where is that? It's on my desktop. This is kind of this classic web page that everyone tends to bring up. Come on, there we go. So this describes pipes. I use this for physics all the time. But we care about a pipe. So we have pipes that are open at both ends, pipes that are open at one side, and pipes that are closed at both ends. So this is what's interesting, is that our room here is considered a pipe that's closed at one end. So is the inside of a speaker here. So the same rules that apply to your room also apply to your speaker. So you can actually still use the same idea of standing waves and speakers. And so that's when we were putting the acoustic stuff in there and some of the damping material. What we're trying to do is disrupt these standing waves in here. Standing waves are bad. Resonance is bad. The same thing, well, not always. Resonance is good and bad. It's what makes a trumpet play. It's what makes a piano play. In that case, we want things to resonate. That's what music is. But there's other times we don't want things to resonate. In the case of speakers, we don't really want them to resonate. We want them to resonate a little bit. That's what the bass reflex is. So actually, we want them, it has an enclosure, so it has a resonance to it, and we're going to use that to our advantage so we can get really low frequency extension. But when we also talk about rooms we don't want resonance there either. If I hit a kick drum, it goes boom. Just like a guitar string, that when you strum a guitar string, it'll ring. Well, so will your room. And chances are you want to hear the music. You don't want to hear your room to some extent. So you want to hear the music, not the poor acoustics in your room. So if we think about this, let's look at what's going on here. It's going back and forth. These are it's a compression wave and a rarefaction. Compression is when the air molecules squish together. Rarefaction is when they pull apart. If we look at this wave, and what we're going to call this is our lowest mode of oscillation, our first mode, it's bouncing back and forth. And so we can imagine, we're going to talk about this just in one dimension today, but we can imagine this in all three different dimensions, is that we have this wave going back and forth in this room right here. And all these air molecules are going to go over here, they're going to squish up, and they're going to reflect off and go the other direction. So, and here's what's interesting, is that when it's a compression wave here, it's a rarefaction wave over here. So and that's going to have some key importance here in a minute, is understanding that there's a phase involved with this. But we can also, if we think about what's going on with the air molecules here, they're all squishing up right here, and they're all squishing up right here. So but as far as how far they move from their original position, we can plot this in two different ways, as a function of velocity or as a function of pressure. So what I'm going to look at, what we're graphing right here is displacement or velocity. Displacement and velocity can be plotted in the same way here. Velocity is how fast the air molecules are moving. Well, if I look at these ones right here, they're not moving at all, right? Well, they can't move at all. They're stuck against the wall. There's nowhere to move. So these air molecules on the end, we're going to call those a node. Well, in this case, a pressure, or this is a velocity node. So they don't even move at the side here. They're not moving at all. But in the middle here, if we look at who's moving, compared to all these air molecules, who's moving the fastest, it's the ones in the middle. And we call that an antinode. So this is a velocity antinode, or right here, it's a velocity or displacement antinode. We can also call it displacement. So how far do they move from their original position? These ones move the most. We can also draw this as a function of pressure. Now, nothing changed with the simulation above, only the way I draw it down below. We look at where's the highest pressure? It's right here. Where's the lowest pressure? Well, it's right here. So now we have an antinode on the sides and a node in the center. This really comes into play. The reason you need to understand this stuff is when you want to start talking about acoustic treatment. You have to understand that how we hear versus how we do acoustic treatment. And I'll hammer on this again for a little bit, but let's get back to the program here. So over here we have no velocity or displacement. We have max velocity in one direction and max velocity in the opposite direction. Over here we have normal air pressure. So this isn't zero air pressure, right? We're not in space. It's just above and below ambient air pressure. Okay. Here's the kicker. We hear as a function of pressure. Our eardrums move in and out based on pressure, not on velocity. If that's the case, and we're looking at these two plots here, we're talking about pressure here. Where is it going to be the loudest? Where are we going to get the most amplitude? At the edges, at the antinodes, right? Right here. So let's take that just another step further. To the mouse, there it is. Okay. So now what we want to do is start talking about in terms of harmonics. So when we talk about things, very few things resonate at one frequency. They usually resonate with harmonicity. So in the case of speakers have that, rooms have that, instruments have that, or my voice has that. We resonate at multiples of the fundamental. So in this case, what I've drawn here is a function of pressure right here and a function of velocity here. Now remember, it's exactly the same idea. And I only drew 1/2 of the wave here. But let's take a look at this right here. How much of one, compared to, like, going back to our original discussion, that one wavelength, or one is one full cycle. How much full wavelength do I see in this first plot right here? Half, because I go from the top to the bottom right here. So I see 1/2 of a wavelength. So in other words, I could say L equals 1/2 lambda. Equals 1/2 lambda. Or, and I can do some algebra, lambda equals 2 times L. So in other words, the one full wavelength is twice the length of the room. You follow me there? So what I'm saying is that this is 1/2 of a wavelength. And we see it also here, 1/2 of a wavelength. So for this to go to a full wavelength, it'd have to be twice the length of the room. So in other words, L equals 1/2 lambda. So if I solve that and I do some simple substitution, lambda equals 2L, and I substitute that into F equals V over lambda, I get F1, and I'm denoting this as because this means the fundamental, our lowest mode of oscillation, is 343 divided by 2L, the length of the room. If I do that, so I'm not going to draw the other one in here, but it's important it's important to realize that this is positive and this is negative phase, that they're opposite phases of one another. All right, so if we do the same thing here, L equals lambda in this case, and our equation becomes F2, our second mode of oscillation is 343 divided by length, which not coincidentally, but it's twice the frequency of this one right here, because this one has a 1 on the bottom, a 2 on the bottom, sorry, and this one doesn't, so therefore this is half of this one, or this one is twice this one. So 2 times the frequency of 1. And then we have 3/2 of a wavelength right here, or 1.5 waves right here. And we solve for it, and this is 3 times F1. What we see is that our harmonics are integer multiples of the fundamental. What I mean by that, it's 1 times, 2 times, 3 times, 4 times, 5 times. Let's prove it. So here's the fun demo. What do you suppose, let's figure out what the fundamental mode of oscillation in this room is right here. For this, I need a tape measure. So unfortunately, I could not find my real tape measure this morning, so I have to go with a shorter one than usual, so I have to do half the room and multiply it by 2. You guys tell me, is that half right there? Yep. Okay. Thanks. So we are at 450 centimeters, or 4.5 meters, so 9 meter width. So 9 meter width of this room. All right, so let's do it with this room. So V equals F lambda, blah, blah. So here's where I take F equals V over lambda. Length is 1/2 lambda, or lambda equals 2L. So I'm going to substitute this wavelength in for this one right here. And I get F1 equals V over 2L. 343 times 2 times the length. So this is where I need to substitute 9 in there. So I have to do this on this one right here, because obviously I was doing this live, so I couldn't type in the numbers before. So what's 343 divided by 18? Anybody got a guess? 19, indeed. You're good. I'll say 0.1 hertz. Okay. Let's go, come on. 19.1 hertz. Is that a problem? That means the fundamental mode of oscillation in this axis right here is 20 hertz. Do we care? Oh, we don't. I don't really care about 19 hertz. I mean, well, you do. I mean, we say that we can hear from 20 to 20K. We don't hear 20 too well. 20 is a pretty tricky one. So, but what I do care about the harmonics. What's the second harmonic of 38 hertz? So to demonstrate this, I knew I was going to run out of time. Okay, so what I have here is something I was super stoked about. Come on. So what I've done is set up a subwoofer over in the corner here. It's just a prototype, an older prototype of one of the speakers I was making. And what I'm going to do is we're going to set this thing up so we can excite the room modes in here. So we're going to have to get up and walk around here for a little bit. I'm going to go back to Room EQ Wizard and use that as my signal generator. So what we care about is 19 hertz. But let's go to signal generator. sine wave. I'm going to go down to, what do we say, 19, so it's 38 hertz. 38 hertz. So if we go back to our room modes here, where do we expect, we're talking about this one right here. Where do we expect the nodes to be? Can everybody hear the low frequency? Okay. We'll get some amplitude there. Make everybody outside go, what are they doing in there? All right. So let's see if this thing is working. What do I want you guys to do? I want you to get up and start taking some laps around the room here and see if you can correlate what you see here to what we hear, to what you're hearing. So where do we expect an antinode to be? Far away and in the middle. So what I'm going to do is, while you guys are walking around, I'll let this thing go for a little while. Walk back and forth. I want you to touch the walls on each side and walk all the way back and forth of the room. And then I'll switch to the third harmonic and note where those nodes and antinodes are. You can walk. You can come up here. You can walk between. It should work anywhere.
Right where you're at.
Yeah, exactly. Really well.
Yeah, right here is fine. Yeah. That's awesome.
I'm going to switch to the third harmonic now. So it's 3 times 19, which is what, 57. Thank you. I'm going to turn it down just a little bit so I don't blow anything up. Okay, now keep moving. See if you can notice where the nodes and antinodes are. Good, that's going. Does it work all the way in back? Are you guys getting it back there? Yeah. It's just called the Fast Track Pro. Cool, why don't we call it good there? We could keep going. But what we end up seeing is, so what do we know? If we start increasing our frequency, our wavelength decreases. And as we go higher and higher in our harmonics, we get more and more antinodes. But the problem is, as we start getting higher in frequency, our wavelengths become small enough that they no longer become standing waves, that they just become ambient room reflection throughout the room. So it's only at these really, really first few modes of oscillation that we really start to see this. So we just went through this. We're going to wrap it up here in just a second. And of course, now what we're talking about is we're only doing this in one axis, this axis right here. We also have modes in this axis and in this axis right here. And so it starts getting really complicated. So you got to start thinking this. But first off, let's think, why are standing modes bad? Well, because they resonate. We don't want our rooms to resonate. But also, we get poor transient response. But also that, obviously, we get different response throughout the room. That's usually not what we want. If you're doing it in a room like this, that means everybody in this room is going to hear a different performance. That's bad. We want everyone to have the same performance. So with that, we're pretty much out of time here. So what I'm going to do is, at this point, we were going to start talking about some more of the high frequency stuff. But really what we care about in the high frequency is the spectral decay. And what we were looking for, what we really want is we were looking for a smooth frequency response, which is going to be part of your speaker response. And so you can actually EQ that out or redesign your speaker if you need to. But then we want to look for a uniform decay. We want to see smooth decay across. If we don't see smooth decay, it either could be a room resonance, or something else in the room resonating, or it could be actually your speaker itself resonating. So in general, we're looking for something around on the ballpark of 300 milliseconds for a smooth reverb time as kind of a target reverb time. So unfortunately, we're not going to have time to talk about acoustic treatment, except in that, how do we absorb low frequencies? Well, absorbing frequencies, we talk about sound moving back and forth. Our goal is to slow sound. We want to add friction to moving sound. So in other words, this is why we tend to absorb as a function of velocity. So what I've drawn up here is, wait, are these my velocity? Yeah, these are my velocity nodes right here. If I want to absorb moving air, where would be the best place to do this? At the antinodes. The problem is our antinodes are right in the middle of the room, right? Putting absorption in the middle of the room is a problem because we need to absorb at the quarter of the wavelength. For high frequencies, we're talking about stuff that's like this high frequency stuff. Putting it against the wall, it's still more than a quarter wavelength of the wavelength, and so you're fine. When we start talking about lower and lower frequencies, that 1/4 of a wavelength starts moving into the middle of the room, and then all of a sudden you're here. So our first harmonic, our second harmonic here. So what we need to do is we need to come up with some other methods. For low frequencies, they're tricky. High frequencies, you can put up pretty much anything, and it's going to absorb it. But moving your treatment away from the wall is going to increase the low frequency absorption because we're getting closer to our velocity antinode. Okay, with that, so how do you absorb low frequency? You can't, absorbing low frequencies is impractical at a quarter wavelength, so we have to do some energy conversion, from potential energy to kinetic energy. Pressure you can think of as potential energy, velocity is kinetic energy. And we need to do some conversion, and that's what panel and diaphragmatic absorbers do. With that, I'm not, because then we start going down, and that can be a whole book written on that. So with that, if this is something that you're really into, I've got 2 books up here that I think are amazing. There's a lot more out there. This is Master Handbook of Acoustics, super, super approachable book. I think this should belong in everybody's library. The Floyd Tool book, it's a little dry sometimes, but it's a really, really, really good read too. I'll have those up here if you want to come thumb through those real quick. But they're both relatively inexpensive books. And with that, I want to wrap it up. So this is my contact information. This is a corny picture of me. So this is our console at the studio. So it's Jeff at merkelacoustics.com or 8housesdown.com or denverdrumroom.com or ucddenver.edu. Or 8 Houses Down is my studio. So the new thing is called Signal to Noise Audio. It's called signaltonoiselabs.org. So if anybody's interested in that, contact me, and we're starting to get people. That Max MSP thing I was just showing off, that's what we're spending a lot of time working on right now, but doing some really pretty interesting stuff, both in sound, but also doing some actual interesting visual stuff too. I also want to give a plug here to Doug Greenlee right here in the corner here. Doug is an acoustician, contractor. He does some great, great work. I'm not an acoustician. I can certainly help answer some questions about that. I'm more of like, I guess, a speaker guy and a physicist, whereas Doug's an acoustician. He deals with true acoustics, and he does actual design and ring outs of rooms all day, every day for a living. So if you have a need for your room or you want to get some information, this is the guy to talk to up here in the corner right here. And actually, I want to thank him, give him a plug for helping me out with some of this material. I also want to give a mad thanks to Matasound. Adam talked before. Matasound has given me tons of drivers to do some. I teach a loudspeaker design class at UCD. I used to. They don't teach anymore. But they gave me tons of drivers and are a really, really awesome company to work with. So if you want to, and I really think you should try making your own. Roll your own speakers. It's really fun. Just don't cut your fingers off with saws, because that's the hardest part. So with that, I want to wrap it up, and let's answer some questions. I know I've been talking for a long time here, but what do we got for? We only have a few minutes here. I think I'm the last one, so we can go forever, but we should wrap this up. So how about some questions? I know it was like acoustics in an hour. It's a tall order. Yes.
Okay, so I'm cheating here because if I sat down with Chuck, I could probably figure this out.
Yes.
But, if I'm going to use a full-range driver, relatively small, 3.5 inches, except the piston probably about 2 inches.
Yes.
That's going to start beaming, and so in terms of propagation, that's going to start beaming at
Absolutely.
Right?
Yes.
Just in that example, so I have a rough idea about what frequencies I can start.
So the way you can think about that is the width. If you think about the width of the microphone or the speaker diaphragm. So you said it's a 3-inch one. So you plug in 3 inches for this right here. So it would be, although I tend to work in meters and stuff. So if you want to find out what frequency, and again, it's a trend. It's not black and white. It cones in as you go up in frequency, and it goes to your 4 pi or your omnidirectional field as you go lower. It's not like it directly translates, but around the width of the driver, as you count that as the frequency, that's when it's going to start switching around. So if you want to think about like what a 3 inches, what's 3 inches? 2.54 times 3 is 6. So, I mean, be over lambda, so it'll be 343 divided by, what's 3 inches in centimeters? Anybody know? 7.5-ish. So just do 343 divided by 7.5, and that'll give you roughly that range where it starts to beam in. What's really fun is to do this, and I really encourage you guys to do this. Take your speakers, take this microphone here, and move it 5 degrees, and take a measurement every 5 degrees, and you'll see it. It's really cool. You can actually see the beaming and and everything. You do these polar patterns. You don't have to do full polar patterns. You can just look at your not your waterfalls. You can just look at your SPL measurements, and it's really, really fascinating stuff to spend time on. Yes?
Correct me if I'm wrong, but I don't think that M Audio has drivers for Linux, does it?
No, but it works natively. It just works. Okay. So it's a little difficult. Pro Audio and Linux don't play too well together. They're getting there, but it's still not perfect. But the M Audio works actually really well. Yeah. Yes, I'll get to you in a second.
If you're treating low frequency nodes with the Helmholtz resonator, then
yes.
you position the resonator at the node as opposed to the antinode?
Nope, you want to do it at the antinode. That's where it's going to have the most impact. The same reason I put the speaker over here in the corner, it's like if you're trying to excite, say, a marimba mallet or a marimba bar, usually you want to strike it at the vibrational antinode. Where is it going to get the most bang for the buck? If I put this in the antinode, I'm really going to excite the pressure antinode. So in the case of a Helmholtz resonator, to be most effective, you want to place it in one of those nodes or antinodes. So, but as we saw as we were walking around, there's multiples of those and harmonics, and it gets a little complicated. The cool thing about resonators is that, well, the cool thing and the bad thing is that they only absorb at about one frequency, so to speak. So you can use them to very finely and accurately tune. The bad part of those things is that you have to custom build them for every single space that you're in. You can't go out and buy a Helmholtz resonator because every one of those has to be custom tuned. And same thing with panel absorbers. They're for that one room only, which is why you don't see like off the shelf low frequency absorbers and active absorbers or passive absorbers because it's specific for that one single room. So, and in fact, you can't just do all theory. You have to do some measurement too. Because if you start adding people, you start adding different things, the rooms don't behave necessarily ideal. They behave pretty well today, but the walls themselves have some give. So they actually throw your measurements off just a little bit too. What I wanted to show with my cool little iPad thing here is that I could sweep. You could sweep within 2% of that frequency, and you can really hear it go and just resonate out there. But Helmholtz resonators and panel absorbers should be put in the pressure antinode. Yes?
Could you go back to the slide showing the books?
Yes. Sure thing. Sorry, I could have done that before. Cool. Well, please feel free to give me a call anytime. That number up there was my cell phone number, so that's the easiest way to get a hold of me. If you want to come check out the studio, we're just downtown. Like this is stuff that I'm passionate about, and I love talking shop all the time about this. And please, if you want to, Signal Noise Audio. Well, we actually just changed the name to Signal Noise Media Labs instead of from Audio Labs because we're actually including more video and animation and that kind of stuff too. We're doing a lot of projection mapping and some cool stuff like that. So, yeah, with that. Thank you so much, and have a great rest of the show. See you guys.